Okay, so good afternoon, everybody. Thank you for attending to my talk. I have quite a lot of material and I asked for a 90-minute talk, so I don't rush it. So please ask questions if you have. This is the first time I present about this library in this setting, and I would like to know feedback and things like this, either during the session or after the session. So we'll see whether we can do generic programming for multidimensional arrays, whether it's possible at all, whether we'll see ugly things in the middle, or it's basically lost cause. I hope not. My name is Alfredo Correa. This is the outline of my talk. I'll give some introduction, motivation. I will talk a bit about generic programming foundations, or at least my interpretation of it. I'm going to talk about array models. I'm going to talk about lazy arrays. That's part of things I propose to solve these problems of arrays in C++. And we'll make the connection with algorithms and performance. And I'm going to talk about the whole context of having multidimensional arrays in the context of computation, right? A bit about myself. I'm a physicist, actually condensed matter physicist. I don't have a computer science background per se. We have been programming computers because we need to do simulations at different levels. Some people is very good at it. Some people is self-taught. Some people come from computer science, but most of us are physicists. So forgive me if I don't get all the nomenclature right. You can correct me, of course. I'm the group leader at the Quantum Simulations Group at Lawrence Livermore Lab in California. I basically do simulations of quantum mechanics, and I have to clarify here that this is quantum mechanics with classical computers, mainly basically HPC systems with GPUs and inter-process communication, network communication, kind of things. Most of my job is actually research-oriented. Anything that we do relative to programming is basically to do some science after that. And in terms of experience with code, I have experience with this particular code called INQ. There is a journal citation here. This is the one I've been working on the last years. I also work in the QMC Pack Quantum Monte Carlo code in the past. So maybe to understand where I come from, I will tell you a little bit about my C++ journey. Again, this is condensed matter physics. Basically, we simulate materials. And the community is historically Fortran-based. So I have been in contact with multidimensional arrays one way or another, and also trying to see whether I can move to other languages. Now, many things are moving to Python, of course, but during my career, I tried different approaches to simulation, basically, right? With many different languages. In some sense, trying to avoid Fortran, to be honest, but I had many false starts with C++. I wasted a lot of years with that. Fortunately, I was doing my PhD in physics at the same time, so not completely lost. Many years wasted doing object-oriented design, pointless template metaprogramming, virtual polymorphism, multiple dispatching, kind of domain-specific languages, kind of things like this. So this type of things I try to avoid, learning from there. Until at some point I found Stepanov works, maybe like a little bit more than 10 years ago. And I understood STL, and everything clicked. That doesn't mean I understood everything, but at least I have a method now. And that's the start of my journey here. And then the question became, okay, so all the community is using Fortran or Python, NumPy, these kind of languages that do multidimensional array language stuff quite well, or at least in a practical way. So can we compete doing generic programming with array languages? And that's kind of the question I'm trying to answer here. For the last year, I have been the secondary representative of the C++ Standard Committee from the Livermore Lab. And I had my first library evolution paper, draft paper with Braden about STD overload. We're working on it, very slowly, but working on it. And I developed a few libraries. One is called Boost.Multi, and this is the one I'm going to talk about today. It's not everything about the library, but the library is an example of how we can bring generic programming and multidimensional arrays together. Another library I work with is, or I developed, is called BMPI3. basically it's a wrapper for the MPI library for inter-process communication or intercomputer communicator in HPC systems. And again, based in C++. And the other one is called covariant. It's a way to do functional programming with variant types. It's kind of in a repository there. But it's related to the STD overload proposal here. So, a little bit of history. If you go to the Computer History Museum in San Jose, I recommend it very much, you will see a wall with this family tree of languages. And of course, at the early years, you have Fortran. You can also see these pins around. Fortran for president, I pray in Fortran, very funny. So, and this is important for me because I have been, especially with senior people in my fields that come from Fortran, I have been trying to explain that in some sense we are in the same legacy, right? That this is not a completely different world. I mean, the languages might look different at first glance, but actually there is a connection between them. And I like this story. It's basically a story that Sam Parent told in 2018. Maybe I'm trying to retell it here with these diagrams as well. So basically at the beginning we had Jean Bacchus, right? In '54, he invented Fortran. And then all the other languages basically came out from there in one way or another. For example, Algol, and then C. And this is completely oversimplified. You saw in the previous slide that there are thousands of languages. This is the ones that matter to this story. Then you have Simula from Algol, and you have Bjarne Struttrup creating C++, right? And after C++, you have Alex Stepanov inventing the STL and coining the term generic programming. And there is a nice kind of intersection here. Basically, at the same time all this was happening here, you had Bacchus receiving the Turing Award. And basically, after 20 years of programming in Fortran or developing also other languages, I think, basically he was tired of the imperative programming paradigm. So in his lecture for this award, basically he tried to kind of say that the functional programming is better. And he proposed something probably didn't work well, what he proposed. But what happened after STL, apparently John Bacchus and Alex Stepanov met I think in the Adobe offices in San Jose. And apparently Sean Parent was there. And actually Stepanov told Bacchus about generic programming, probably showed some examples. And according to Sean Parent himself, Sean Bacchus was very impressed. He knew that he needed to figure out how to work mutation into functional programming. And for some reason, generic programming is functional programming with a well-defined way to handle mutation. So apparently he had his own interpretation of what generic programming meant. I mean, I think it's a nice goal to have, so I wouldn't argue with that. But yeah, so another piece of trivia, apparently Bacchus promised Stepanov to write the foreword for this book called Elements of Programming with Paul McJones, but unfortunately he passed away before writing this foreword. But it would have been a nice closing of the story, in my opinion, if that would have happened, right? And the main reason I put these languages here and then lists here is that what these languages got right in some sense, Fortran, C++, C, is that they basically interpreted the machine as an array processing machine. Right? So basically they embraced that from the beginning. Not necessarily multidimensional arrays, but at least acknowledging that arrays are fundamental to performance, for example. So the other thing I learned from reading Stepanov is that you need kind of some philosophy to develop, right? And no mathematics. And he actually, in one of his notes, these are all available online, he debates against programs that are not mathematical. He says these programs are insecure, these programs crash, programs that cannot be easily modified, and these are these examples of programs that are not mathematical. And he says, worst of all, that there is an economic reason for that. One is job security at a small scale and world domination at the other. I don't know, I mean, there are many interpretations of what he was referring to, but in my opinion, in perspective, he probably was referring to, I mean, if you know STL, to this idea of making frameworks. And this is what I'm trying to avoid in some sense. Basically, provide a library for multidimensional arrays that tries to do everything. And if the library provides what you want, then you get it. But if it doesn't provide what you want, then you're on your own. That's kind of terrible. And that's kind of my small-scale world domination part. He also said, guys, we should use formal methods even when we write XML stuff, which I find very funny. And actually, there is a little bit of XML in this talk later. Okay, so why do we need multidimensional arrays? So every time we discretize space, for example, and do partial differential equations in, for example, in two-dimensional and three-dimensional grids, you need multidimensional arrays. In quantum chemistry, you have matrices, you have tensors to represent quantum states. If you do signal processing, let's say you have windows of time, and inside each window of time you have frequencies. If you do machine learning, many of the data that is fed into the machine learning algorithms actually are fed as multidimensional arrays. The other reason is performance. Usually, basically, when you work with multidimensional arrays, you have the possibility of data being contiguous, or at least being regular in memory. So you have some efficiency gaining from that, especially cache efficiency. Then you can go further and have CMD vectorization, you have GPU parallelization, and then you have many libraries that actually work assuming that you have multidimensional arrays, like BLAST and LAPACK, and then more modern ones. And the other thing is that arrays are a natural abstraction in general, so many different languages, even they have different libraries, different data structures, or different paradigms, they can always communicate through arrays, especially one-dimensional arrays, but also multidimensional arrays. So if you write the program in MATLAB, you probably will be able to save these arrays in a way that NumPy can load them and things like this, right? So it's a lingua franca of data structures as well. And, well, C++ STL basically doesn't give you multidimensional arrays, but it gives you arrays. So it's mostly 1D operations which you can do with STL. And that's kind of the gap here, that the language never had standard multidimensional arrays, and that's kind of a blessing and a curse at the same time. Because a blessing, because a curse because people had a lot of obstacles to use multidimensional arrays in C++, and a blessing because probably if they had put that in the language, they would have gotten it wrong in the first try. So that's great. So what are the multidimensional arrays? So typically with multidimensional arrays, what happens is that people don't know anything about it, they never use it, they will never use it, so they don't care too much. And then people say, okay, I'm an expert in multidimensional arrays. So I'm doing a balance here. The idea is that you have data that is arranged in a regular pattern in 1, 2, 3, or 4 or more dimensions. And that's kind of the idea, right? So for example, you have an array here of 3 elements, an array here of 2 by 3 elements, an array here of 2 by 2 by 3 elements. And then for 4 dimensions, it becomes even more difficult to visualize. And if you want to have an interpretation in C++, let's say element 1 if in A is B, B12 is N, right, here. And then with the first one, you select the plane you're in, the second, the row, and the third, the column, so its value is here. And take into account that the visualization is only a convention in some sense, or you can say that the notation is a convention, either way. But the point here is that there is an implicit symmetry between the indices that you want to maintain in general. And that kind of guides some principles on how to implement these data structures. The other thing is that even if you have separate things of separate dimension, you want to have relations between them. I mean, this is something that you naturally will expect. For example, you would like to compare whether this array of 1 dimension is the same as, let's say, the first row of B, right? This is the assertion here. You can compare for equality or inequality, these kind of things. Then you can ask for subarrays of a 3-dimensional object that is 2-dimensional, so this would be like a cube concentrated here. and then compare with whether it's equal to another two-dimensional thing, right? One note is that most of the examples here are in 2 dimensions for simplicity, but you have to imagine that what I'm talking about is actually the n-dimensional generalization, and that's what I implemented. So from my work, motivation for multidimensional arrays, what I do is simulations of matter at extreme conditions, and that includes fast particles going through metals, for example, and how they affect the electronic density. The way we have to represent the electronic density is basically this 4-dimensional object. It has 4 dimensions because you have the position and time, and you discretize over those. And the density is a real quantity. And this is basically the quantity you're seeing here, except that there is some transparencies you can see through, right? But it's a 3-dimensional object that you're seeing at each time. And this is based on quantum mechanics. So electrons are described with wave functions. The wave functions are complex numbers. You operate over these complex numbers, right? Turns out that these wave functions have 5 dimensions now, because now you have the position, 3 dimensions, time, and then you have a new index for each of the electrons, and you can have thousands of electrons. And then when you construct one object from the other, you might need to do a reduction. And in this particular case, we actually do simulate things in a dense representation for these arrays. So there are no shortcuts here, in that sense. And I didn't even say how we obtain these wave functions, how we propagate it in time. But basically, it's a partial differential equation, again, for which we had to apply fast Fourier transforms, linear algebra, MPA communication, and of course, nowadays everything has to be in the GPU. I lied a bit here because time is actually not something that we store unless we are making a movie. So everything is 4 dimensions and 3 dimensions at each instant in time. But you can see the need here. You're dealing with many different dimensions. You're dealing with operations on these dimensions that are element-wise, so it can be reductions. And you're dealing with different kinds of numbers, real numbers or complex numbers. So this is kind of the ideal ground for generic programming that allows you to abstract yourself from many particularities of the elements. Right? You can store real numbers, you can store complex numbers. Okay, so C++ and multidimensional arrays in 2026. There is a keynote tomorrow by Mark Orman. He's here, thank you for coming. On making standard C++ standard parallelism multidimensional. Please attend. I don't know what it's about yet, except for the title, but I'm sure it will be good. There's another talk in this conference type linear algebra, which is probably related in some way. There is this library called Parrot that was created this year or the year before, I don't remember, by Connor Ostra from NVIDIA, in which he touches some of these ideas as well. There is also CUDA tile that will be soon available for C++, of course, in addition to all the CUDA ecosystem for arrays. And then there is my library, Boost.Multi, the one I mentioned before, that maybe is fully accept in Boost. So far is conditionally accept. And we'll talk about that a little bit. So is 2026 the year of the C++ and the standard array language? I don't know, but maybe. So one of the definitions of generic programming is that we should start from the concrete and then generalize. Another interpretation of this is you should start with what works and then abstract or generalize. And what works for multidimensional arrays, at least in some subspace of application, is to have a certain representation of this data structure as what is called strided arrays, or at least this is how I call it. Basically, the idea is that memory in the abstraction is a linear set, right? And you have to, in some sense, wrap it around such that you have multidimensional structure to it. So in this simple representation of a multidimensional array, a 2-dimensional array in this case, basically you put each element contiguously in memory until you run out of your row, right? And then you go to the next one, right? And then basically what you have to do to go through this array or access each element is to do operations on on the strides. Meaning, if you want to move to the right or to the left, you have to change your pointer by 1 in general. But if you want to go up and down, you have to change your memory by 6, for example. Right? Now, if you want to access now a subblock, and I don't see the colors here, this is terrible. So you have to imagine a smaller array here. It's colored in my screen, but not here. But you have the numbers at least. What happens is that now you have a subarray that goes from index 1 to 3 in this vertical dimension, the row dimension, 1, 2, 3, and that's excluding the 3. Basically, this is a half open interval. So you have 2 elements by 4 elements, and this is the array you're seeing here. Now, this new array, ironically, has the same strides because you have to move 1 to go left or right, and you have stride 6 if you want to go up and down. But then there are other things that change in the representation of the array. First, there has to be some kind of extra numbers that will tell you the size of the array if you want to ask about it. You don't need these to access the elements, but you need them to see if you're out of bounds, for example. And then the more important thing is that also you're changing your base pointer. So basically now your initial address for this is maybe conveniently moved into this 0, 0 element here. So basically you have to take the pointer you have originally in your V array, and then the subarray will have this pointer plus 7, which is 6, and then plus 1 here. So note that here I'm not talking about iterators or ownership or memory management or anything. I'm just trying to construct some kind of algebra of layouts. These are called layouts that basically describe a subarray with respect to a large array or things like this. So this is kind of an operation at the end that you have to discover for each of the subgroups that you take from the original array. You will need to compute these new numbers in some way. And this is kind of the mapping you do to refer to different elements effectively. Now, the one I showed before maintains the dimensionality. The one I'm showing here, again, the colors are not showing in the main screen. You access a row of the array. So row 1, right? So row 0 is this one here. Row 1 is this one here. And now what happens is that to describe this layout, you actually leave less numbers because now you have a single stride, right? And then a single extra number that will tell you how to reconstruct the size of things like this. So one interesting point is that actually this array here that is one-dimensional, is basically row 1, is not an object that actually exists in memory in some sense. It's in the C++ sense. Of course, you have an idea that B1 or B row 1 is a subset of B, but at the same time, there's not a single object that is there. And even if you think that this memory here is an object, then remember that these numbers can be runtime. So there's not such concept as an element that has a runtime size. This is kind of some of the obstacles that the language kind of gives us, compiled languages give us. So in the same way, let's say you're talking about now the third column, right? So that would be, you will transpose B and take the second one, or you bind the second argument for the access, the coordinates for B, and then you leave the first one as a wildcard. And actually, this is kind of sneaking in the notation I'm going to use during the presentation for the library, the notation I propose. So this is real notation later. Not the T, but this one here it is. So now what happens is that now this one-dimensional object is represented in a different way. Now when you go from one element to the next, you will have to shunt 6 elements in real memory. So it would be a shunt like this. And yeah, so basically this solves in some sense what you need to do each time you want to access the original or the biggest array you have in your problem, right? You can have several of these, but each time you access sub-elements or sub-arrays of the ones you have, you will have to do these mappings of one layout into another, and that layout can change dimension or be the same dimension. Usually it's lower dimension. Another exotic case you have, let's say, if you have, you specify the subarray to be from row 1 to row 3, right? So it's only 2 rows. And then from 1 to 5, excluding 5, so you will have some kind of subblock here. But then if I ask for a stride, which can be passed as a third element in this notation, it doesn't have to be this way, but basically what happens is now that you have a smaller array that doesn't have stride 1, right? So you have stride 2 and stride 6. There is no element in the middle for the two-dimensional, the subarray of this bigger array. So you have one element here, one element here, one element here, one element here, but you don't have nothing. You have anything in the middle. That's why these numbers are here. Actually, this should be 1, not 2. Okay. So the advantage of this layout is that now accessing elements is very simple, right? Basically, you take your base pointer and you apply multiplications and sums to get your new location, right? And I think the most important thing of this layout is that it's symmetrical between the indices. Of course, it cannot be completely symmetrical because this stride 1 and stride 2 have to be different numbers. So one would be bigger than the other and things like this. But at least the logic of accessing through one index, meaning one dimension, or the other index, meaning another dimension, then is the same. And that's what allows you to generalize these two n dimensions quite easily, right? So that's the first pro, right? Usually what happens is that as a result of taking subarrays of arrays and things like this, what you have is the memory remains fairly compact. It doesn't need to be absolutely compact, but at least it's regular. That's kind of the big advantage, because hardware can take advantage of the regularity. And very often it's contiguous as well. So you can take advantage of that once in a while, or actually very often. Another advantage is this is compatible with many libraries, high-performance libraries that are made especially for specific hardware, including FFTW for fast Fourier transforms, BLAS, LAPACK, CUDA-FFT, CUDA-BLAS, MPI, and many other libraries for high performance. So this is kind of the data structure you should use if you're interested in high-performance computing, at least at some scale, right? So the cons it has is that it's not available in the language as it is, so you need library solutions, and of course when you need library solutions, then you will have many libraries, you will have different interpretations and different solutions for this problem. And we have to admit that there is no support from STL algorithms. STL algorithms don't know anything about multidimensional arrays. There are some multidimensional data structures, but usually there are implementation details. But there is not much support there. Right? The other one is that it's not easy to grow, at least not, I mean, if you have an array, how you grow it symmetrically in all directions is kind of harder than in one dimension. And this is not to say that there are no other data structures or layouts that actually also preserve symmetry between indices, like tile or zigzag or Hilbert curve filling. These kind of things also are important, but they are not completely different from this one in the sense that it still is regular access in some way, and also there's kind of an implicit symmetry between the different indices, which is something that you usually want. So what's the wrong way to do multidimensional arrays? Of course, the first thing we try when we start with C++ is, okay, we have this standard library, we have these vectors which can compose and put anything in them. So you put a vector inside a vector, and then you say, okay, I'm going to maintain the invariant that these things will be rectangular, so they are not ragged, for example. That's fine. So what pros do you have? Well, you have this notation, Bij, for example, works out of the box, which is very attractive. The other thing is that you have iterators. So you think you're doing the right way because now you have iterators, you can apply some algorithms to them. But everything starts to crack there because you need to access things in the right way to use iterators. You have to first access the first index in some sense, first and not the second. So there's this asymmetry between the different dimensions. They're easy to grow, right? But I would say that these pros are actually traps, really, because they're terrible in any other metric. They have distinct logic for different dimensions. The memory is all over the place, so you don't have, even if you don't care about allocations, accessing a column of these arrays is going to be a nightmare. And it's not compatible with the libraries I talked about before, right? So you don't have to implement your own FFTs or things like this. And it gets worse with higher dimensionality. So some foundations. So I mentioned in this diagram of languages, this very nice book, Elements of Programming. And I start here because I want some kind of idea how to, now that I know what is the structure that works, how to formalize it in a way that works well with algorithms, and we can construct something more mathematical in some sense, or formal, right? Turns out that Stepanov, one of the gems in the book, and it's one of the simplest parts of the book, to be honest, is this definition of Alex Stepanov of regular types. So he starts by defining semi-regular. Basically, he says semi-regular types are default constructible, they're copy constructible, and they're destructible, and you can assign them, right? And the idea of presenting this kind of classification of types is not because he wants to say, oh, all types have to be this way. He's trying to make the connection between these syntactic properties of the object and assuming that you have the right semantics according to him as well. Once you have these two things, then you enable algorithms at each stage. For example, the first connection he makes is that he says, if you have a semi-regular type, you can swap. He can swap as an algorithm. And of course, it's kind of a building block for many things. So that's kind of the important point of view here. That by using this classification, he has a mapping between certain kinds of types and the algorithms you can use on them. Then he defines regular. He says, if you have semi-regular, but you have also equality. Again, he doesn't say all types should have equality, but if they have, you have some new algorithm that you enable, which is linear search. That's kind of the idea. If you have regular and then you have order, right? Even in C++20, you have ways to enforce these properties of having order in a way that is blessed by the language in some sense. He says, okay, once you have order, then you have binary search, for example, and you have sort, right? What happens if you have total order now, which is basically same as partial order, but now if something is not less or greater than the other, then it has to be equal. Well, you have the same things, but it can be more efficient because you don't have to check for the third case, you don't have to check for equality, and things like this. So the claim that he makes in the book is that these regular types are amenable to equational reasoning. And in my opinion, the modern C++ is in some sense is based around them. Again, it doesn't mean that all types have to be this way. It has to be like you have to have this kind of reference frame in which you have to at least think about some regular types in your program, otherwise you're completely lost. And I don't know if who proposed this or if I got it from somewhere, but basically I have this litmus test for new types. Every time you have a new type in your library, usually you try to do something exotic and something kind of smart, supposedly. Well, let's try it. If you can put it in a vector, right, and then you can sort the vector and you get the expected result, then you probably are in the right path with respect to this classification. You have a regular type. You also have total order. But the point is that if you have something that you think that should behave in a nice way, and you can also add order to it, maybe, then this is a very quick test to do. It's not exhaustive, of course, but actually you wouldn't believe how many types that you see in the wild actually don't have this property, because they try to do something funny with equality, for example. So let's say you have I don't know, some kind of invented library, cuckoo library, and you have A and B objects, and you say A equals B, and they say, oh, the copies are expensive, so I'm going to copy a pointer So now that A now points to B, right? Well, first of all, now you are outside the semantic requirements of the assignment of the regular type, because now you have objects that are not disjoint, in some sense. And also, worth of it, sometimes you need a copy, so you need to have another function for a copy, and you will call it something like dot copy, and there is this inflation of the syntax, right? Because you have to force the copies, for example. And all starting because you wanted to avoid them, right? So another thing I'm going to introduce here, and Stepanov doesn't talk too much about it, although there is some hints of this in his book. Basically, saying what do you need for a type to represent the value, right? And in some sense, my interpretation is that it needs to be regular, and it has to have some Platonic kind of existence, right? Which in practical terms can be persistency, right? So if you have the number 5 exists whether or not the program is running. So if you can save it to the disk, right, or send it somewhere else, right, and then the other one can take that and then give it back to you, you should have the same value, right? So in some sense, and I think Sean Pallant actually proposes this, that the natural extension of regular is something that is serializable. And unfortunately, there is no single way to do serialization in C++. So everybody invents its own way. So you have a save and load, or you have a print and read functions. You have off streams, shift to the off streams and then read it. There are some libraries, of course, and I'm going to talk about that very shortly. But the point is that there is no standard way to serialize C++, and worse of it, there is no generic way to do it. So we have to adopt some convention at some point. Okay, so now the library. The library has been, I have been calling the library for many years, and in early 2026, I proposed it to Boost. Matt Borland from the CPP Alliance helped me to set up the GitHub repository, which was a requirement for the Boost review, and also helped me to put all the documentation in a certain format that is extremely nice and searchable, and things like this. So now you have access to it. This GitLab and GitHub are exact mirrors of it. The main reason I have to use both is that the CPP Alliance is providing me with the CI machines in GitHub. In GitLab, I have basically GPU machines that test the code in GPUs. Okay, so why did I propose this library to Boost and not the standard or Bman? And by the way, I love the Bman project. So I can promise backward compatibility or some binary compatibility. There are many ways to represent this, and it's a work in progress. There will be a lot of controversial idioms that I'm going to introduce in this talk, and that's why you have this hot pepper there, spicy pepper. Not because you shouldn't push back, but just to acknowledge that I know they are controversial. So you will see some examples. So I think there are too many restrictions in standard that they wouldn't work with well with other libraries outside the standard itself, like these ones here. And also there is also already span, std span, std end span, std end array. So what's the point of stepping on each other's foot, right? And also the time horizon is very different. I'm stuck with C++ 17 and 20 mainly because of the use of GPUs. So I cannot wait to 26, for example. So why I propose these two Boosts instead, I think it's the right balance between risk and innovation and the quality that they expect from a library. It's peer review. I come from scientific research. I think peer review is the gold standard. It's the worst system we have except all others, in some sense. And I think it has a nice model of distribution, and we have the visibility there. I don't need specific things from the compiler or anything, at least for now. And it has a nice time horizon. I can develop it as it's being reviewed, or it's being accepted, or it's being released at different versions. And also it can benefit from kind of having a peer kind of relation with other libraries in Boost, like Boost HANA, Boost Assert, Boost Align, and Boost STL interfaces for obvious reasons, as you will see. And also with Boost serialization. I think serialization is a very important thing. It's not only practical, I think it's fundamental, as I said before. The other libraries are JSON. This one is quaternion vector matrix, so there are some connections there. And then there is YAP, which I think does expression templates. So I don't do expression templates in the library, but in some sense, if I design things well, I mean, somebody else can combine it with YAP and then do expression templates. I don't think expression templates is solution to many problems at all, but. Okay, so I don't want to convert this talk in a tutorial for the library. So I wanted to just show kind of the trade-offs I had to do when I designed the language, the library, and to give you an idea of the implementation of it, right? So to generate an array, you select your type for the element, int in this case, and then the dimensionality, which is here too. And then you choose the size for this. And these are runtime sizes. All the sizes in this library are runtime, by the way, with some caveats. You can initialize this also from initializer list, which is very handy for debugging and showing examples. That's kind of a nice feature. I had to work hard to make this work, to be honest, but at the end it works pretty well. The other way to generate an array is to actually refer to someone else's memory, right? Instead of relying on your allocator, which is completely implicit here, you basically pass for this reference array some data that somebody else allocated. In this case, it's just an array of 12 ints in the stack, but it can be something provided by another library that allocates memory or is already working with some other object that you have some idea how it behaves with respect to multidimensional arrays, and you want to have your own representation of it. And again, you choose also the size. So probably this data has at least 12 elements. And then you access these elements, right? So element 1, 2, let's say, can be assigned the number 5. Element 1, 2 can be assigned the element 5. You need cplusplus for this syntax. This is a multidimensional square bracket, I think, the proposal. And then you have this other one, which is kind of more strange, because now you have also the same coordinates, but you have split this into two operators, right? And there is this idea that maybe there is an intermediate object here, which is true. But this kind of exposes the fact that the library actually can refer to elements not only to the int level, but also at some partial dimension. So for example, A1 by itself can be row 1, as I showed in the illustration before. But now it's a concrete library actually implementing this. So, and this is where the first kind of ugly thing happens. You have your original array, which is 4 by 6 in this case now, for some reason. And then you want to take the first row of this array, right? As I said before, this object in some sense doesn't exist, so it cannot be a language reference, this second row of the array. So what is it? The truth is that I have to invent some kind of proxy subarray reference type, and that's usually the solution for these kind of things. The problem is now, so the question is, what do I put here? What's the type of this row object? And it can be kind of misleading here now already, because of course if I want to use a subarray, I will use a specific type of the library to represent subarrays. They shouldn't own the memory, for example. The problem is that, for example, doing this is too verbose, right? By the way, this should be int here, not double. This is too verbose. The other thing you might want to do with a row is actually to make a copy, and that will be fine, right? And if you don't want to be verbose, you have to use auto, right? Which is misleading now, because auto usually means that you have a copy of something, right? But actually here you don't. So, and this is what Scholl-Falco and Herr-Sutter identified as a problem in 2017 already, that basically you have these misleading things that return a reference-like object or a proxy object, and you don't want auto to mean actually the proxy object, but actually a copy of it. So they actually wanted the right-hand side of this equal to control what auto means here, instead of being completely automatic. And that's what they proposed in this paper. I think the paper was mostly ignored, and some people, I talked with some people, and some people say this is not a problem, right? But I think it is a problem, right? Now, if I were to generate an iterator for this, now it wouldn't be that bad, because the iterator can be anything. The iterator can have all the information to reconstruct the row. But once I dereference this iterator, I will have the same problem. Right? So this is what I'm trying to show in this slide. So the solution I found in the library, and this is the first hot pepper there, is that we can be specific if we never use the auto row equal to some reference. So what I propose is to use one of these three options. The library provides a unary operator plus that basically makes a copy, a new object that has the copy of that reference. And this is equivalent to say, okay, I want now a one-dimensional array object that is a copy of the first row. And if not, then basically document the fact that you have a reference by using either ampersand or ampersand alone, right? And the same thing, and this is almost the same thing for functions. If I want to take generically a function that takes an array, the only way I have to basically take anything, can be an array or a subarray or a consubarray, is to actually have this forward reference or universal reference thing. So this is kind of analogous to that. This is completely opt-in, and I cannot enforce it. So if you don't want to use this, then you don't need to. In C++14, I had a way to enforce that you couldn't use this. Basically, it prohibits this auto row, but they remove it in 17, so now I cannot do it. Some people don't agree with this, so that they don't need to use it. So as long as you know what you're doing, it's fine.
So do you mind just going back to it?
Yes.
So there's a reason that you chose this path, because this is different than, say, if I make an STD vector, I can make a span that uses its elements.
Yes.
And yeah, if the vector goes away, the span is dangling, but as long as the vector is in scope, I don't have that problem. But if my slice operator returns a view object, normally view objects are passed by value. They're pointers, right? And so if I have a reference to a pointer that's kind of more dangly than the original pointer.
Yeah, so this is kind of the, yeah, I see what you mean. So for example, this is an alternative. If you don't want to have like templates everywhere, you can use a concrete reference object.
Well, I guess what I want to know is like, what was your motivation for diverging from the vector span design?
I don't like the semantics of span to begin with.
Okay.
And I think dangling reference is always going to be a problem. So it's not something that you solve in some way here. I mean, you can have workarounds and solve it partially, maybe with fixing certain types. But yeah, this is the controversial part of doing this lifetime extension. But I never found any problem with this. That's kind of an argument from experience, to be honest.
I mean, my experience with when I see libraries that take arrays by template $ampersand by forwarding reference, that usually suggests that the library was meant to be generic on whether the input is a view or a copy.
Yeah, that's exactly what I'm proposing here.
I see. Okay.
Yes, and that's the main reason.
Yeah.
It just turns to be analogous to when you name a reference. Because at the end, what you want to do here is to name a reference. Not here, sorry, the second and third line. That's kind of the motivation to have a line like this. For the most part, if you don't need to name a reference, don't name it, just say A1, right? But sometimes it's complicated, so it makes sense that sometimes we have to put a name to the reference. Yeah, so as I said, it's controversial.
Well, I mean, you're not, a lot of times when you create a slice, it's because you're passing the result as a parameter to a function. So even though the BLAS was written for Fortran programmers, it's meant to be used in that way. So the function arguments to the BLAS are slices. And so you don't have to name them, but you are creating them in order to pass them in.
Yeah. because you're creating these new strides from
Yeah.
an original one.
Yeah.
Yes, and that's the information that these objects carry in some way, the second and third.
Yeah.
This doesn't carry it, it's just a new copy. But yes, so in some sense, the name references is just a way to store the new stride layout and put in a name to it, and then make it look like a reference in some sense. If you don't like to use references, you can still use pointers, iterators. You can say, like I put at the beginning here, a begin plus 1, right? But now you're at a different level of semantics, right? And there is a mapping between the two. One is the reference, and the other one is kind of taking the address or something like that. So what do we do with the library? For completeness. If you have a multidimensional arrays and you take the first, and these are the fundamental ones, and then the other ones derive from this one. That's the interesting part. So you can bind the first, the value of the first index with brackets or parentheses even. You can slice it, meaning that you choose a range in the leading dimension. This is all in the leading dimension. You can transpose, for example, meaning that your indices will be swapped, the first two indices, and then you can rotate or unrotate the indices. And also you can stride in the leading dimension. So this affects only the leading dimension except for rotate, which access the other ones. So it turns out that anything else can be written as in terms of the ones in the previous slide. For example, parentheses is the same as bracket here. This notation of having first and last is basically forward two slices. If you have first, last, and some stride, you will do some slice first, and then you do stride. And this is all implemented in the library, basically. Now, if you have a wildcard, you bind the first element. This is the same as this, it's the same as this, right? If you are binding the second argument, basically you rotate first, you bind the first argument, and then you rotate again. This kind of stuff. I think there's a mistake here. Okay, partial. So let's say you have a partial range in the first dimension and a given index in the second one. Basically, you bring it the last index forward because of rotate. You evaluate it, and then you do unrotate, and then you do the first last. I think these unrotated here are not correct, but you understand the idea. Basically, you write everything in terms of the fundamental ones that I showed before. So first criticism is that there are too many temporary objects here, especially if I implement this in this way, and that's true. I mean, technically there are temporaries, but the compiler can completely erase them or elide them or whatever is the word. And I tried many different compilers, and they're very good at actually eliminating all this intermediate code. And I have some examples in the documentation and in Godworks to show you that the code is actually what you expect. And then again, in cplusplus you can use square brackets if you like that better. Okay, so the other problem that you usually have with multidimensional arrays is the problem of aliasing here. And this is kind of the simplest form of aliasing, what I'm trying to show here. So basically, this is also an illustration of transpose. So if I have an array that is 3 by 3, and then another array that is 3 by 3, and I transpose A, and then I assign to B, what do you expect B to happen here? So basically, B will be A transpose, right? The question is this going to allocate? And the answer is no, it's not going to allocate because B already has the right size. And the library checks for that, so it doesn't need to allocate. It's no different from what std vector will do. If you assign another vector with the same size, it will just copy the elements without growing the vector. Now, if you assign to an array that is empty.
Wait, clarification.
Yes.
So that assignment doesn't need to allocate, but it does copy the values?
Yes, it copies the values. Yes,
Okay,
so if the value is allocated,
you're
it's
not
true.
creating an alias?
Yes,
Okay.
so it doesn't allocate here because it's an
That's the more important thing than
Exactly, yes, that's a good point. I always forget about that. These other semantics in which you copy pointers. You don't copy pointers. So B is not a view of A. B is B, it's separate from A. That's kind of one of the philosophical points of these libraries, and I think all that what Stepanov showed us. Right? If you have an equality, it should be a disjoint object already, a copy. So if you have C now that it was empty to begin with, You transpose, you assign, then it's going to allocate now because C doesn't have the right size. And well, the library will handle all that for you. You will have access to the allocator you pass, at the construction, and then work with it. Now, this is the tricky part. So if you have A transpose and you assign to A, what do you think happens here? Well, the result is that it's probably garbage. Maybe if you're lucky if it's a square, but I don't think it happens. So this is kind of undefined behavior. In some sense, it's undefined by the library what happens here, because I cannot guarantee how this assignment will happen, in what order, and things like this. And 99% of the time, you will never get the transpose, actually. So the question is, what do you do? Right? So basically, trying to do an in-place transpose. This is an advanced algorithm that you need to implement here. The library doesn't try to do that. The library tells you, don't put assignments and refer to the same things on the left-hand side of the equal and the right-hand side of the equal. That's kind of the aliasing problem. The good thing about the library in general is that you only need to worry about aliasing across an equal sign. It doesn't take input-output parameters such that you have FAB, right, in the library at least, and then you say pass FAA, and then it's going to be a problem if you pass the same array twice. You have aliasing there. The next thing also here is that I can make this work. It won't be the most efficient thing to do, but it's important to make it work first. And then I use the plus operator again, the same way I used it before, now to materialize an array from the right-hand side of the equal. So what I'm doing here is I pay the price of an allocation, and then an assign to A. And this is guaranteed to work. So you have an equal, then you might look for aliasing. If you have a plus after the equal, then you know that the library is forcing a copy there. And I like this idea of basically controlling, make it equal mean copy, but at the same time controlling the lifetime or the materialization of some of the copies. So there is this dual purpose of operator plus. It helps auto, and it also materializes subarray references if you have this problem. So how is this? So how is this designed in the library? So I have all these introduced many different objects, starting from array and also mentioning subarray. Turns out that when I constructed the library, I started using inheritance for composition, which is usually a bad idea. I recognize that. But it turns out that for this example, it works really, really well, amazingly well. And I don't know why, because any other attempt that I had to use inheritance for composition was a failure. But I think this idea that some of these objects are actually representing referencing themselves makes this work, right? And that's kind of a discovery for me, surprise. Not only that, I made this inheritance public because I found it useful as well. Turns out that when you have a subarray, it's in itself a non-mutating subarray, right? So you might get to this kind of object-oriented conundrums of, so a subarray is a const subarray? Well, that's not the interpretation. The interpretation is that if you have a subarray, you might choose never to change it, so it fulfills all the properties of a const subarray. So you can convert it into a const subarray. Okay, so ownership is pretty much what you expect. It's no, right? And then you have this new dynamic array. I may talk about that later, maybe not. And then you have an array which owns the stuff. As I said, it's not copyable. And this is a diversion from span here. It's not copyable on purpose. There's no copy constructor. And I think that's kind of the principle here, that something that is a reference can never be a regular type. So don't put the copy constructor because it's going to mess your semantics. That's my thesis here. So can you move from these subarrays? No, because these subarrays the elements of these subarrays belong to another array. So you don't move from it. If you do swaps, of course, if it's a const subarray, you cannot swap the elements because they're const. But these other ones, you can mutate the elements, so you have swaps, but then it will be order n. And then you have that, except for the last one, the other ones can be resized. So this is kind of the recursive structure I mentioned at the very beginning about the relationship between different dimensions, different objects. So you start from an array, let's say you do operator indexing, you get a subarray of lower dimension. If your original array was const, then you will get a const array. The constant in some sense is codified in the type. That's usual in the STL as well for const reference or const iterator, something like this. You can also do dot begin, and you get an iterator of whatever dimension. If your array was const, for example, then you will have a const iterator that will constrain what you can do with that. Now, if you have a subarray, you can take an al begin there, and then you have a const iterator of even lower dimension. The other thing is that these subarrays, and we touched on this before, are usually R values. Most of the time, they are created on the fly. So one surprise that I have to overload, for example, begin ampersand, to make this work. Because if I don't overload begin ampersand, then for a newly created subarray, even though the original array is modifiable, or the elements can be mutated, then it will go the route of begin const ampersand and go to a const iterator. So this is another property of reference-like objects, that they like to have their own ampersand operations being overloaded as well. And it's a need in some sense for this framework or for this point of view. So now operator plus, the ones I showed before, in case you need it, you don't need to use it all the time, but if you want to materialize a subarray of lower dimension, you do operate the prefix plus and you get the array. And then I take this opportunity to introduce two other types here. One is, so let's say, so then another one is to do operator parentheses and then put a range there from, let's say, 1 to 5. This doesn't lower the dimension, but what you obtain is not the original array, but it's a subarray that doesn't own the elements. And then you have this subarray pointer that you create back and forth with some operator ampersand, and this should be like a big hot pepper as well here. And then you go back with operator asterisk or dereference. And then another one that is important is elements type, which is basically is a view of the original array that goes through the array in a linear fashion. It's a flattened array. It's very useful. It has all the same information as the original array, but now you have a new range that is completely one-dimensional. It's segmented now, but it's one-dimensional. And then you can apply one-dimensional algorithms to it. Sometimes it's useful. Yes.
Operator that takes an index range. Sorry to interrupt.
Which one?
That one on the left that goes kind of down below, one below.
This one.
Yeah. What does that do if it doesn't reduce the dimension?
Well, so let's say you take one dimension, right? So you have for elements from 0 to 10, right?
Yeah.
And then I want to have the subrange from 4 to 7.
Yeah, that part makes sense.
Yes.
Like,
so
what about if it's two-dimensional? What does that mean?
Oh, it's in the leading dimension. So you have, let's say, 10 rows.
Oh, I see.
And then 20 columns. And then you take only the first 4 rows.
Okay.
But you still take the 20 columns.
So it's like you did the placeholder for the second dimension.
Yes,
Okay.
exactly.
Oh, okay,
Yes.
I got it.
So subspan in just one dimension.
Yeah.
Yes.
Okay, thank you.
Yeah, I'm sure you have something similar in this one. Okay, so it looks complicated. I have to accept it. But maybe this is a minimal, complexity that we expect from arrays. Maybe we have to live with it. And that's kind of my point here. So it looks complicated, but maybe it has to be this complicated. It cannot be simpler.
I do have another question.
Yes.
Sorry. So, like, you talked about, like, your design is deliberately not the vector span design where you're allowed to create views and views are semi-regular.
Mm-hmm.
But you do have iterators here, and your iterators are semi-regular, or actually regular.
Yeah, they're regular. Yeah.
So
They are not values, but they are regular. Yes.
Do you experience conflict between those two things? Because iterators are kind of like views, but they also need to be regular in order to work with the
I think they match perfectly in some sense, because I can have the regular non-value type that is the iterator.
Yeah.
I can have the non-regular type that is the subarray.
Okay.
And then when I need to materialize something that is a value and regular, then I materialize it into an array.
Okay.
So I have these 3 layers or 3 options all the time. And most of these operations are efficient. I mean, except for materializing, all the rest is something that you switch back and forth. And actually, the next sample is exactly this. Oh, again, no colors here. So we have to imagine something. So you have the original array called B, and let's say you have an algorithm that detects some kind of special regions in this 2-dimensional array. So one is from this corner here, right? Another one is here, and another one is here, right? And then let's say your algorithm detects this and is very good at it. It might be written in C or something. And then you say, I want to store these subarrays or these subblocks because they're important to me to process later. So the question is, how do you store these subarrays? And my pedantic answer could be, what do you mean by storing subarrays? You cannot store subarrays because they are valuable. Well, the point is that the library will help you to actually find out that you cannot store subarrays in a vector because it doesn't pass this litmus test I mentioned at the beginning. They are not copyable, so this will not even compile. But you still want to store them at these locations. You don't want to go through storing a lot of numbers. So my point is store the pointer. Store the pointer to this subarray. So you put an ampersand on front of it. And then you generate this type here. Yes, and it's hugely controversial because I'm overloading operator ampersand. Now, I'm overloading operator ampersand, parenthesis, ampersand, ampersand, which doesn't exist in the language because you cannot take the address of a temporary. But these arrays, the subarrays from the point of view of the language are temporaries, and I'm taking the address of this temporary through the library in some sense. But it's all fine because this is a very well-defined thing. It's a subarray pointer. For many purposes, it looks like an iterator, but that's a different story. So what do I do with these pointers to the subarrays? Well, I can store them in a vector, no problem. I can copy the vector, I can grow the vector, I can do whatever I want. Actually, the type of this vector is going to be a vector of subarray pointer. And then after that, I can iterate over these subarray pointers, right? Get one by one the subarray pointer, singular, and then do something with it. And then here I'm sneaking in how to use elements. Basically, this is a pointer to a subarray. I do the reference for that, I take the elements for that, which is a flattened way of looking at this, and then set them to 0. Okay. There was a fun question here, why I cannot parallelize this, but it's not very funny now because you don't see the overlaps. The point is that these original domains I was showing here that I'm not showing the screen actually overlap, so you want to serialize them. But that's a different story. Right. The point is, you can store subarrays if you understand that you're actually storing a pointer to these subarrays. And this kind of solves a problem that Tony Vanier actually introduced or actually detected in 2018. He wrote this P paper, P1085, in which he did everything with ASCII art. So he says, should we make span regular? And he has this Yoda phrase here. His point is that, well, we should have two types, spanning pointer and spanning ref. This is exactly that. And I swear, I found this not long ago. So I found the same solution. Actually, what happens also is that once you have these two types, I have in my library, the way I design them, is that they are deep const, for example. Any const that you put in front of any of these types will lock as immutable anything that is inside, at least in that context, like reference do. And it has deep assign. So you have a deep assign here as well. So it kind of goes through this tree and then basically goes through, I think, the solution he wanted. And the nice thing, so the original problem was one-dimensional for the span, but it gives you the opportunity to actually revisit these problems in multiple dimensions, which is nice. Okay, we're going to skip that. So this looks complicated. Everything I'm putting here is complicated. So can I show you that it works? Again, so there are thousands of tests in the library trying to, explore corners and explore notation and things like this. But I show you at the beginning this litmus test for arrays. So the array is actually a value, and my proof is this one. It has ordering as well. I didn't talk about the ordering, but it has lexicographical ordering across dimensions. It's recursive. So let's say you have 3 arrays. These A1, A2, A3 are 2-dimensional arrays each one, so you have to imagine blocks. And then you can sort them, and then when you finish sorting them, they are sorted. So it passes the litmus test I defined at the beginning. Now, I have another test, which I call the acid test. or the shim-parent test. And this is something I invented. At some point, shim-parent said the old STL algorithms exist in the original version of STL at least, exist to implement stable sort. So the point is, if I have a container or a range or something like that, that works with a sort or with stable sort, it probably works with all of the STL, because sort will call stable partition, will call rotate, will call swap, probably many other things I'm not writing here. This test looks a lot like the one before, but it's quite different, because now what I'm actually proving here is that there is an iterator interface for the array itself, or even for a subarray, doesn't matter, that can take advantage of algorithms and still do the right thing. And this was kind of the challenge. And this, in the first days when I started the library, this was my goal actually, to make an algorithm like, not because I need sort, but because I need to actually show that it works with many parts of the standard library at the same time in a very short, concise way. And it worked very nicely and efficiently for me to code, because I could see in every step where the semantics of the iterators or the subarrays would fail partially sometimes, and then correct for that. And that's why I had to introduce all these hot peppers or this controversial stuff sometimes to actually make this work. So that's the story. So one is the litmus test and the other one is the acid test. Again, more chemistry analysis. So there is a bonus test, which is now, I'm going to do the same, but I'm going to do it with the view now, with A transpose. Oh, by the way, so you see the original array here, now it's sorted, right? Lexicographically sorted. So what happens if you have the same array now, and then you transpose it, and then you sort it, right? Well, it ends up sorted, right? But it's being sorted column by column, right? That's kind of what I'm showing here. So it's kind of a bonus test. You have litmus test, acid test, and the bonus test for views. And this is the kind of challenges I like to subject the library through to actually say that I'm in the correct path. Okay, how much time I have? 15. So as I said, in my opinion, serialization is very important. And the reason is because this was actually what makes a regular type a value officially. And the way I kind of bring that to the library is to basically taking these two libraries that are quite similar, both serialization and serial, and then see what are the common patterns they have, and then kind of from these two define what I call like generic serialization. Generic serialization, what allows me in particular, is basically bring the library multi and not depend on any library that is serialization. So I don't carry the dependency from serialization or serial, but it works with both. The advantage for my practical day-to-day is that I can do a lot of things at the level of the archives of the serialization library. For example, I have another library I mentioned at the beginning. It's called BMPI3 that does MPI packing, for example. I don't want MPI multi to know anything about MPI. I don't want serialization. I mean, I cannot make serialization know anything about MPI, but I can create a Boost serialization compatible archive that can do serialization to MPI packs. I have another archive that's called archive YAML, which serializes to YAML. And the only thing I have to modify is my own custom archive types, which are based on the ones that are provided by the library. The serialization provides binary, XML, and that's it. And also, these ones I provide. I think text, I forgot to put it here, pure text or something like that. The serial can serialize into JSON, XML, and binary, right? And these are the ones provided by them. But I can extend it at this level. So now I can communicate or do stuff like writing to files without multi knowing anything about how to do it. This kind of thing. So, see, didn't I say that it would be some XML? It's here. Okay, so the other one that was important, and this is not so much about generic programming, but actually enables a lot of genericity in some other dimensions, is support for allocation. So values need to own the objects they have, the elements they have. So the idea was to make it work with classical stateless allocator, work it with scope allocator. Let's say if I have nested arrays. It's not that I need this every day, but the point was to prove that I could insert the scope allocator and then pass this allocator to the elements. And of course, this new polymorphic allocator. And actually, this is something I use. For example, if I have tie loops and I need an array that lives in the middle of this loop, instead of creating it and destroying it all the time, what I do is I allocate first, and then the object, the value inside the loop will use the memory that is pre-allocated. And this is very nice because it separates one of the main criticisms of value semantics is that you make many copies and you make many allocations. But with these techniques, you can actually separate the memory allocation from the creation of the object. So that's kind of the way I see it, right? In terms of generic program. Another one you can do is fancy allocators, for example, interprocess allocator, like Boost interprocess allocator. You can memory map these arrays into your disk or something like this, or share it between processes. Actually, this is the first one I supported besides Classic, because we have some needs in the context of MPI. We want to have MPI processes in the same node to share the same arrays. And then you have special purpose. You have device allocators from Trust, CUDA, usually it's a GPU pointer, what you have here. And actually have even shortcuts for the names of these arrays that take this type of allocators, called the multi-trust device array to follow the same convention as trust. And then I also support the memory resources allocators, which are fundamental for the codes I mentioned at the beginning, because at the time we started, memory allocation with CUDA was extremely slow, but we could generate a pool, right, and use these memory resources.
You fixed that somewhat.
Yeah. But then
that's what CUDA malloc async is for.
But then we moved to AMD.
Oh, I can't help you with that.
No, but yes, that's right. But I think the memory pools are a good idea in many contexts anyway. So.
Yeah.
So as I said before, so allocation gives you basically memory from here or there. The question is, so it answers the question where? Where are you? Where is your elements? Can it answer the question of how to process stuff? And it turns out that it can, because one of the most important properties of an allocator is the pointer type. And it doesn't have to be a raw pointer. That's something interesting. And actually, Trust embraces that. So when you have a device allocator, which is most commonly GPU, it can be other things, but then you get a pointer which is a device pointer. That means that every array that I declare with this allocator will have at compile time, in some sense, information about where this memory is. So when I call an algorithm, it knows it will have to, well, sometimes it's constrained to, but it would prefer algorithms that run in the GPU directly, right? So this is what I'm kind of exploiting here. And I didn't show any implementation details. This is the only implementation that I'm going to show. Let's say you have two different codes. One that is a normal CPU code, it uses STD allocator, and then you assign A to B, right? Copy, basically. Copy A to B. And then you have another piece of code that uses the trust device allocator, right? Now, these are using the same library. This array template is the same as this array template. So how does it know how to assign A to B? Basically, how does it know that what copy it needs to call? If I hardcode STD copy here, then it will be bound to use the CPU version that the standard library provides. It will crash for GPUs or something like that. Well, actually, it won't even compile because the pointer types inside these ranges are going to be device pointers, and STL will not know what to do, I think. Well, I think we'll catch them and then try to dereference and explode. And this is kind of the problem that many people from NVIDIA are trying to solve as well. I mean, to bring standard parallelism into the normal code so everything looks the same. That would be nice. But the point is basically here. You have two allocators. You have the library in the middle. And in some sense, this information about the types of these pointers will choose which algorithm the library uses. I could use ADL here, right, argument-dependent lookup, but it's extremely fast, right? Because let's say if I say copy n, it will call std copy n most of the time. If anything here matches the standard namespace, but if things are trust-like, then it will call trust copy n if trust was included already, which is another problem. But sometimes some elements here might have both namespaces. So for example, if I have a trust pointer that refers, it's another good example, to an std complex, then that object lives in both spaces and ADL will fail there. It will be ambiguous. Right? So the way I solve it, and this is a hack, is completely kind of an implementation detail, is to have basically this function object ADL that has kind of a generic function call, right? And it generates a priority for different, versions of copy n. The first of which is maybe your iterator can have an internal copy n member function. And if it doesn't have it, this will fail because of SFINE and go to the second one. And this will use ADL. But if ADL fails, we'll go to the next one. And then I had to make a choice here. I put trust first because trust can handle CPU if it's available. You don't need to compile everything with trust. That's the other thing. So this line might or might not be here. And at the end, as a last priority, I use the std copy. So that's the way I solved this problem. And
Cocos actually has a similar.
Cocos.
Cocos has a similar problem with Cocos View Deep Copy. And so they choose, in typical Cocos fashion, they like to have traits for things. And so they have traits that you customize to define what it means. But yeah, it's the same problem.
Yeah, that would be, yes, that would be the principal solution, like adding another parameter here that tells you about the policy. But the problem is that you have to have a policy for each algorithm in some sense, or some kind of execution parameter for this. I might add that. This is maybe wants to be too automatic, but so far it's working nice.
Yeah, it's a design philosophy. Like Cocos doesn't want to be automatic. Like it wants to be explicit, and your library wants to be more automatic. So it's kind of
I mean, the objective is actually what you see exactly here, that you have CPU code and you port the code by changing just the allocation, for example. That's it. So this can be two versions of the same code at different times. First you have these, and then you just change the allocator, and then hopefully everything works. Okay, how much more time we have? 5. So I'm going to, I have a nice material about something that I call restrictions, which are lazy arrays. This is kind of, looks like the ranges library inside Multi. This is from some inspiration from SimParent, an email that I exchanged with him, where he said, I want to initialize arrays from coordinates. And I thought, okay, maybe you want to set an array from a lambda or something like that, or put the lambda in a constructor. But it turns out that these are two bad ideas, actually. What I needed to introduce is some kind of special range that evaluates a function and returns, and it behaves by all means like a multidimensional array. So and that's what I solved in this part of the library. It enables a lot of idioms that are very nice. So I'm going to do a simplified case for parallelism. The nicest one is after this, but there is not enough time, it's complex. Let's say you have a 3-dimensional array. This has 250,000 elements, for example. And this is a real cube, actually. Imagine that it's filled out with elements inside. And you typical old style code, you do like a triple loop, and then you do some operation, and let's say this operation is costly, so you want to parallelize it. So the first thing you try is to put an algorithm. We're not savages, so we replace the for with a for each, and not much gain there. But then you say, okay, same timing. Maybe now I can parallelize, right? And the timing goes down, and by a nice factor, right? So you're parallelizing something here. So the next thing is, maybe I want to have everything in the GPU now, and I want to keep doing this and parallelize again with respect to the first one. But remember, this array is 64, 64, 64. So in the CPU, it's not a big problem because you can divide this big cube in, let's say, 8 layers and then do parallel on each one for each CPU or something like that. But for trust, you actually want to parallelize over as many elements as you want, and you're restricted by 64 in the first dimension. And if you do this with the second dimension, it's also limited by 64. So you're not taking advantage of these. Actually, trust is very nice because this doesn't compile. It doesn't like all this idea of proxy objects in the kernels. I mean, outside it's okay, but in device functions it doesn't like it. So, but even if it could compile, it wouldn't be any gain actually, because it won't parallelize almost anything, right, with respect to the power it could have.
So your proxy objects are not trivially copyable.
So again?
So it's because they're not trivially copyable?
Maybe, I don't remember now.
Like,
but
okay.
Yeah, I had to look at it again. So the idea is, okay, so you have this dot elements function that I showed before, and it's very powerful because it flattens your array. And basically you're fusing all these loops through the library now. That's the next thing. So the evaluation of the identification of each element, let's say if you have an array that is not contiguous and it has strides, we have some, for example, integer divisions, which are slow. But what you gain by parallelizing this is so much more that this is actually the correct way to do it. And this is the kind of thing you gain, right? I mean, it's like a factor 10 with respect to the original version. Don't take this timing seriously, it's just an illustration. Now you can go back to the CPU version and say the same for each, and then flatten all these elements, and then parallelize over that. Now you have more opportunities than just dividing 64 in your original range of 64. Now you have your range of 500,000 elements, and you can divide them in whatever chunks you want, or the library can do it, right? The STD for each bar. Right? So nested loops, like you have reference value. If you do STL in the first dimension, of course, you don't mean anything. If you do parallel STL, you can have factor 2 if you do it in the leading dimension. If you do trust for each for the flat elements, you have this factor almost 10. And you can go back and say, okay, for each with the flat elements, it's a factor 4, so it's even better than this for some reason. But now if you, let's say you go to a single for each, yes?
When you did with your NVIDIA GPU, where was the memory placed? Did you
that's a good question. So the tests are done in this machine, and probably this includes the swapping of the memory even. I don't remember. That's why I wanted to have something fairly large. So that's why I say don't take these numbers very seriously. I think the ordering is correct. Now, if you do for each, and this is the only price you pay, if you do for each for flat elements, then because you're paying for these extra operations, then you have kind of a detrimental effect. But the point is that you want to do everything in parallel. So you want to flatten out all these arrays as much as you can, and then fuse the loops. Yeah, so this is the kind of what I propose. So you have your code, how you port the code. You take your loops and you convert them into algorithms, and this kind of a discovery kind of phase here. Then you flatten your algorithms as much as you can with dot elements and dot extensions. This is kind of techniques that the library has to refer to flatten access and use lazy arrays that I didn't talk about. And then you insert your parallel routines here, or your parallel policies, and then once you're sure of that, then you can switch to trust, and then in trust you can explore other algorithms. And that's actually the next example, which I'm not going to go through, but it's basically a way to do row-wise sums using reduced by key, which is something that is not in the standard library, and it's an important use of trust that you can even exploit in the CPU, because trust can support threads in CPU as well. Basically, the idea was to propose a new algorithm called reduce by row that is applicable to arrays, and internally implemented as reduce by key using all the features of the library, like these lazy arrays that I didn't talk about, and this flattening of the elements, and and all the iterators that these multidimensional arrays give you. So that's kind of a nice summary of how everything can come together. And this is kind of one generic programming to do, actually. So that's why I like it. So, so the reason one here is that keep looking for algorithms even after you are here, because once you are in new custom library, you might have more algorithms than in your original STL. So that's what happened to me for reduced by index, for example. Once I switch to trust, I have access to more algorithms. Okay, so I have something about adapters for BLAS, LabPack, FFTW, QFFT, CUDA BLAS, etc. And the takeaways, so generic programming seems to work for arrays. You have to make some concessions. That's my take. You have to be creative a bit on how you interpret iterators, subarrays, pointers to the subarrays, these kind of things. You create copies, views all the time. You make copies when it's convenient for you. And the idea is to compose and expand STL or use STL-like libraries. You can do it with this kind of approach to multidimensional arrays. And also this kind of discovery, I would say, I don't know, that basically by switching allocators, sometimes you can port the whole code and make it work just changing the allocator, because the backend, and that includes even BLAS, switching from BLAS to CUDA BLAS, for example, can be handled by the library as well, because all the type information is in the pointers at the end, or most of it. And you have the documentation here, the two links, GitLab and GitHub. If you want to know more, that's it. Thank you so much. Questions?
Does Boost.Multi has any relationship with Boost.Multi array?
No, it's not based on that. I mean, I used multi-array for a while. I think it has some kind of design flaws that were impossible to overcome. And that's the inspiration for this library. Of course, at the time, it was revolutionary, but it has some glitches and some semantics that is kind of tricky. But for the most part, in some sense, this could be a successor for it. But it's written from scratch. Yeah.
I mean, I have maybe unusual opinions about arrays. And probably, I know your talk has opinions about arrays. My talk has, my thinking has completely opposite opinions from arrays. But I think part of that is just I see a lot of principles in your design, and that's good. Like,
yeah.
I like that. Like,
Well, thank you very much for appreciating that part,
yeah.
because maybe that's the most important part.
Yeah.
That I try to force certain principles. I mean, it might
Yeah.
lead me to some kind of dead ends or nowhere,
Yeah.
but I kind of exhausted these principles, if I can say that.
I mean, usually people scold me from my opinions. Like, I don't believe that in dynamically allocated value arrays at all.
Uh-huh.
I think they should be move only,
Uh-huh.
and I like how SYCL controls access to things with scope, and a lot of people don't share those opinions with me, and so when I try to write that kind of code, they get mad. So I know how it feels to have opinions.
Yeah, yeah. Yeah, these is things we can experiment. We can create another type that is only movable and things like this, and see how it fits in all these categories.
Yeah.
Many of these intermediate kind of implementations that I have in this hierarchy, this inheritor, in some sense, it's like they come in for free. In some sense, you can have something in between, let's say, subarray and dynamic array that is movable only or something like that, right? And experiment with it as much as you can. Don't expect it to be able to put it in the vector, but maybe you don't care about that.
Yeah.
Most people don't care about that, to be honest.
Yeah.
But yeah. Okay, thank you.